So here, let's get into the three-dimensional stress and strain from uniaxial stress on uniaxial strain. Let's now shift our focus to the multi-axial. Welcome to the real world. So the real world is mostly on the axial or 3D. So Cartesian coordinates is like the default coordinate systems. And how many stresses do you have? And out of which, how many are normal stresses or direct stresses, and how many are shear stresses? So what is a direct stress and what is a shear stress? So here so is sigma yy, it is normal to the area. So is it a direct stress? And sigma yx or sigma yz, it's parallel to the area. So is it called as shear stress? And what about sigma xx? It's normal to the area. So is it called as the direct stress? And is it tensile or compressive? So tensile is when you're pulling it, it may be subjected to tensile stress. And when you're just compressing it, when you're applying loads, trying to squeeze it, it comes under compressive stress. And the shear stresses are sigma xy, sigma xz, and sigma yz. These are the shear stresses. So these shear stresses are caused by shear forces that are acting parallel to the area. And the normal stresses are sigma yy along the y-axis, sigma xx along the x-axis, and sigma zz along the z-axis. So why is it that you can call it a sigma x, but why do you call it a sigma xx? It's because that the first subscript is for the direction. So the outward normal to the plane on which the stress acts, and the second subscript refers to the direction of the stress arrow. So here it is norm. Whereas when it comes to shear stresses or the complementary shear stresses, the first one, if you take sigma yx, so in which direction is the outward normal? And in which direction is the stress arrow? So sigma yx. So the direction is, when the direction is towards x, it is called as sigma yx. The direction is towards z, it is called as sigma yz. Similarly, when it comes to the stresses and shear stresses in the corresponding to this particular phase, sigma xx is the normal stress, where the first subscript of x refers to the direction of the outward normal to the plane. And that is the outward normal is if this is the plane, the outward normal is x-axis. And the second subscript refers to the direction of the stress. So about y-axis, it is sigma xy, and about z-axis, it is sigma xz. For simplicity, In most problems, the first and second subscripts can be interchanged. Sigma xy is equal to sigma yx, sigma yz is equal to sigma y, zy, sigma xz is equal to sigma zx, the complementary shear stress. So here what we have is the stress matrix or stress vector, and this contains all the stress components. And the first three are normal stresses, and the from 4, 5, 6, these are shear stresses. In the first three, these are normal strains, and these are shear strains. Three D strain definitions. So here we have 3D multi-axial problems. The uniaxial definition for strain as del L by L is not applicable. 3D strains can only be defined in terms of displacements of the domain. The 3D direct or non-shear strains are related to the displacement components as follows: epsilon xx, epsilon yy, epsilon zz. Note that the use of partial differential symbol del in the above equations is intentional and indicates that the displacement ux, uy, and uz can be functions of x, y, and z. The notation and sign convention used for strains are the same as those used for stresses. That is, the tensile strain elongation is positive, while the compressive strain is negative. The 3D shear strains are defined as follows: the half factor in shear strain. Two definitions are often used for shear strain, one with the half factor and one without. The shear strain definition with the half factor, this is the mathematical shear strain. And when it comes to continuum tensor notations, let's use this. And if you take the normal engineering shear strains, so you won't observe this half factor. So both these definitions are valid. So let's see for a particular problem how both make sense. So now here you have the Hooke's law. Hooke's law for uniaxial case would be sigma xx is equal to epsilon xx is equal to 1 by e sigma xx, or sigma xx is equal to e into epsilon xx. When it comes to three-dimensional, so if along x-axis, if it is if along x-axis, if it is tensile, the other two axes might be of compression. That's why you have this negative sign, and because of Poisson's ratio effect, you might have compression on the other two sides. So that is why you have negative notation, negative sign convention that denotes that the other two sides are compressed. And a little addition to this would be thermal strength, which is alpha into delta T. Delta T is the change in temperature, and alpha is the thermal property, that is the coefficient of thermal expansion. So now you have, so this is said, this is epsilon x y, epsilon X, Z and epsilon Y, Z, these are shear strengths. So the shear modulus mu can be defined as E by 2 into 1 plus epsilon. So here in computational mechanics formulations, it is often more convenient to place stresses on the left side of the equations. There is stresses expressed as functions of strengths. So sigma is equal to D into epsilon. There is elastic property matrix. D is the elastic property matrix, or the D matrix is what connects the stress and the strain. So in linear FEA, you will always observe this. Stresses are expressed as functions of strains. And how do you get these strains? You get the strains from displacements. So this D is also called as stiffness matrix. Stiffness matrix is what connects the stress to strain. And how do you convert displacements into strains? Let's look into those equations later.